As I mentioned yesterday, one of my challenges and slash missions is to try to figure out how to incorporate more cognitive STEM education into the STEM guitar course that I have at Kankakee Community College. But before we get started today, I have to have a word from our sponsors. Our program this afternoon is brought to you by Banaka the Breath Freshener. One drop under your tongue keeps your breath fresh and clean all day. And by Preparation H. Well, we can't talk about that one. Just don't get the two mixed up and you'll be okay. Okay, caps and coils and reactive components. And again, like I said yesterday, because the STEM guitar course is more or less a survey of STEM topics, and you don't have students in there for a whole semester specializing in one topical area, you kind of have to skim the surface on some of the STEM studies and do more with metaphor and general concepts and things like that. So students I get in my class are not electrical technology students. I do have a lesson that precedes this on basic Ohm's law and things of that nature. But then we talk about components in an electronic circuit, and I distinguish between the passive components and the reactive components. And I say your standard passive component is a resistor. It's going to be whatever it's going to be, whether it's a DC circuit or an AC circuit. It does not care what kind of signal goes on there. The ohms is the ohms is the ohms. Whereas we have two other components that react very differently, whether they are in a DC circuit or an AC circuit, hence called reactive components. But those are our coils and our capacitors, and that reaction that they have in an AC circuit specifically is dependent upon the frequency. I also like to point out, what are they really? And if you look at the schematic symbols for these, what the heck is a coil? It's just a stinking piece of wire. And what do we call a piece of wire? We call it a short circuit. And look at the capacitor. What's that? Well, that's two wires not even touching. What do we call that? That's called an open circuit. Okay, so we got a piece of wire, we got an open circuit. But because of the way they're specifically built and shaped, they react when there is current applied to them or current moving back and forth across them. And I point out how they're actually the opposites of one another. Coils and caps are mirror images. Coils love steady state current, meaning that once the current is established, it's just a piece of wire that passes the current. Whereas capacitors, they hate steady state current, meaning that it's not even going to pass. You put a DC current on there, you try to, you got nothing because you got an open circuit. Coils hate changing current. They abhor changing current. And the faster it changes, the more they hate it. Capacitors love changing current, and the faster it changes, the more they love it. When DC is turned on, a coil is itself a short circuit, but when you first turn DC on, it acts like an open. Momentarily, we don't get into time constants yet, but for 5 time constants, it acts like an open circuit, and then it becomes what it really is, just a piece of wire. Whereas a capacitor, which is an open circuit, when you turn it on, it first acts like it's a short, and then it becomes the open circuit it really is for a short period of time. In DC, coils pass DC, but they kind of, and I put it in parentheses, they act like they're blocking. They don't totally block it, but they act like they're blocking AC, they resist it. And while a capacitor, I put this in parentheses, appears to pass alternating current, it's used all the time for blocking because it's an open circuit. And we'll talk about that here in a little bit. So when we talk about the reactance, one of the characteristics of these reactive currents is the way they resist things. And in the world of reactive currents, we call these resistances reactances. So we have inductive reactance and we have capacitive reactance, and notice again they're the opposite of one another. So the special AC resistance that coils have is called inductive reactance. The special AC resistance capacitors have is capacitive reactance, and opposite of one another. You can tell by the inverse. With coils, the higher the frequency, the more they resist. Whereas with capacitors, the higher the frequency, the more it seems to pass the current. So this is about the tone control in our electric guitar. So we need to focus on that reactive component called the capacitor. A lot of people don't know that capacitors used to look like this. Originally they were called Leyden jars. And a Leyden jar is basically a glass jar, foil on the inside, foil on the outside, a little stopper in there with a metal ball on top and a metal chain that goes down and contacts the foil inside. And oftentimes they would ground to the outside and use this for storing charge. And this is what I mean by the capacitor's an open circuit built in an odd way. It's got this huge surface area which can pile up and gather a bunch of electrons on one side. And a lot of people have never noticed in this famous painting, there's a Leyden jar sitting right there at Ben Franklin's feet when he's trying to suck down lightning. And if we had more time, I'd love to tell you all the stories about, because Franklin was a member of the speculative Freemasonic movement. He was a Rosicrucian when he was in France. He was a member of the Lunar Society of Birmingham. He studied the ancient wisdom teachings, and he believed that the universe was filled with a primordial ether. That's what they called it back then. Now it's called the neutrino sea or whatever you want to call it. And he called this thing a condenser because he believed that he was condensing down the body of God into this electricity. It was a condensate of the ether. And still today, I remember when I was a kid working on lawnmower engines, we had points, so we had a condenser. Well, the condenser is really just a capacitor. Now, how is it that this funny shaped open circuit acts like it does? And with DC, I like to think of it as a balloon. If you have a real small balloon, or a real small capacitor, and you go to blow into the balloon, you're not going to have a lot of luck if it's real tiny. But if you have a very large, empty, loose balloon like this, and you take a big breath, it'll almost be like when you first put the breath in, like there's nothing there. It's like blowing out into the air. But the more you blow into the balloon, it builds up pressure, and it gets harder and harder to put air into the balloon. Eventually, when the pressure inside the balloon is exactly the same as the pressure you're able to push with, you can't put any more air into it. It becomes the open circuit that it really is. Now, with alternating current, it's not really that it's acting like a balloon. Imagine this: two compressed air tanks with a pipe in between the two. With just a pipe, and they both have pressure on them a little bit, pressure is going to be the same in both. However, making an electrical metaphor, if we want to move current back and forth, we need to have an alternator, an alternating current generator. What if we could have a little air compressor to provide our pressure that could pump air back and forth between the two tanks? And you get the students thinking about this metaphor. And you say, okay, now, what if I'm moving it back and forth real slow and I've got real small tanks? Well, I'm going to get over here and the pressure's going to build up before I even finish the stroke, and it's going to stop. But what if I do it real fast and cycle it real short? Well, it's going to be easier. What if I make the tanks bigger? Oh, it's going to be easier yet. And you can start to get the students to see, without understanding all the physics, although they kind of are understanding physics, you get them to see how a capacitor really works. Now, here's a schematic with our tone control in there. And the way our schematic works is it takes advantage of the fact that the capacitor hates DC, and DC is nothing more than 0 hertz AC. So the lower the frequency is, the more it fights and resists it. But for high frequencies, and the higher the frequency goes, the less resistance is there. It seems to pass right through. So what we're doing here with this guy is, if you put the proper size capacitor in there, it basically will shunt off, because it makes path of least resistance, it will shut off the high frequencies. And again, remember yesterday I did the tuning fork thing, and I said you can't test the tone control? What that was all about is the oscillating frequency from that tuning fork is a pure tone. But when you pluck the string of a guitar, you have this rich fullness of all these harmonics and overtones, multiple frequencies, and some are way up in the high range. So when you're actually tuning your tone control here, when I reduce the tone control down to 0 resistance, the only thing there is this causing any resistance to that shorted path is the capacitor, but the only thing that's going to short off is the higher frequencies in that rich volume of vibrations. And that's why when you turn that tone control, you get all of a sudden a more mellow or a warm tone, because all the highs are coming off because of that capacitive reactance. And we call this a low-pass filter because it's only shunting off the high frequencies. It's allowing, or I should say, forcing the low frequencies to go over to your load, to go to your jack. There's too much reactance or resistance for the low frequencies to take the shortcut, so they all go to the jack and off to the amplifier. And that's how our tone control works. In essence, what's going on here with the pot is, if you crank the pot all the way up, it's just a big resistor then. It's such a high resistance that everything goes to the jack. As I back off on the pot, I'm allowing more and more of the high frequency to come on through. And it's called the cutoff frequency. The capacitor sets the frequency at which the amplitude of the signal is going to drop off for those high frequencies. And this shows the pot at different degrees of increment on the tone control. So if I have the pot turned all the way down, well, there's my cutoff. Whoa, those high frequencies are dropping way off. But if I turn it all the way up, I mean, to high resistance, I'm hardly losing any of the high frequencies, and I keep further volume, if you will, all the way across the spectrum of frequencies. Now, one of the things that happens is when you're building a guitar, if you want to play warm, mellow jazz, you're not going to want the twangy tone of a country western guitar and vice versa. So what you can do is you can actually select capacitors of different sizes. 3 minutes. You can select capacitors of different sizes to go into your guitar depending on how you want the tone control to work. So one of the things I've thought about is, what if you take an arrangement of various capacitors like this, and you just clip them into the guitar and allow the students to choose. So what we have right up here in class is Tom's guitar, which had a shorted cap in it, and we cut the cap out, and I put in a couple alligator clips where the capacitor would go. So now I'm not paralleling on, I'm actually selecting a couple of capacitors to go in there. And is it on? It's on. Is it warmed up? Oh, there we go. Too loud? No. Okay, so
Never.
let me put on a capacitor. And I'm sorry I threw these into my bag Friday before I left, and I don't know what the values are. But here is a capacitor right here. There's a volume control. Here's a more tinny sound. Hear how the tone changes? Now, let me change caps. Let's go from that to this. Different size cap, which will give us a different cutoff frequency. Oh, that's the volume. Much more dramatic than the other one was. And so here's an interesting thing you can do with your students. You can set up like this, and you can allow the student to choose what capacitor do they want to put into their guitar. In fact, Tom, I think this one's kind of nice. We might solder that one.
Yeah, we might solder that one in.
Yeah, I think so. So that's something that can be done in the classroom.
Time.
That's time?
Yeah.
They get experiential feel for, what did I do with the controller? They get experiential feel for how this thing actually works. There's some typical ranges. There's some other topics that you could discuss in class, and have a nice day.
You had to put that in there.